Hello everybody, my name is Bryce McCourt. I am an online student at Grand Canyon University, majoring in chemistry education, and this is my active learning presentation over the ideal gas laws and gas properties for the concepts of physical chemistry class. So the following are the student learning objectives. The students would need to know what is expected of them that they would need to know and learn and take away from a presentation, from a lecture, from anything instructional. And so for this following presentation, students will understand the properties of gases and their connections to the ideal gas laws. Students will analyze the relationships of the different gas properties. Students will collect data regarding the changes in these gas properties, and students will create graphical representations and will make connections regarding the ideal gas laws. So background information before the students would have to dig into the assessment is for gas properties. There are multiple ones of these gas properties. For example, there is pressure, that is force over a given area. There is volume, which is length times width times height of a gas. There is temperature, which is the average kinetic energy of particles in random motion within a gas. And then there are the number of particles in a gas. And we normally refer to these number of particles as moles. And so for an ideal gas law, we would have to assume that the gas is ideal, which means that the point masses are moving in constant, random, straight line motion. But we also have to have some well-known assumptions for ideal gas laws. We have to have some well-known assumptions for a gas to be ideal. And one of them is that the particles have no forces that are acting upon them. And then the other assumption is that these particles, they do not take up any space. So their atomic volume is ignored with ideal gases. We are going to assume that gases are ideal for this case, for the ideal gas laws, but in reality, there's something called the real gases. There's real versus the ideal. And the real gases, we do consider that the particles themselves take up space. We don't ignore the atomic volume, and we also do not ignore the intermolecular forces or intermolecular interactions that are acting upon the particles within a gas. But again, just for this case, we are working with ideal gas laws, so we are going to assume that under all these conditions that the gases are ideal. And then we also go under the kinetic molecular theory, that the gas particles are in constant motion and they exhibit perfectly elastic collisions, and that the average kinetic energy of a collection of gas particles is directly proportional to the absolute temperature. And so to get to the main ideal gas law, we have first a few laws that first combine together for the ideal gas law of PV equals nRT. So first we have Boyle's law, and that is that the pressure and volume are inversely proportional. So for example, if I would increase the volume of a gas, inversely proportional means I increase the volume. That means that the pressure would decrease if I would keep temperature constant in that case. Next, we would have Charles' law. And Charles' law says that the volume and temperature of gases are directly proportional. So, for example, if I would increase the volume of a gas, with pressure being constant, then that means I would increase the temperature of that particular gas. Third, we have Gay-Lussac's law, which says that the pressure and the temperature are directly proportional if I would keep volume constant within a gas. So, for example, if I would increase the temperature, that means I would increase the pressure of that gas. And finally, we have Avogadro's law, which states that the number of the particles or the number of moles within a gas and the volume of that gas are directly proportional. If I would increase the number of moles within a gas, that means that I am also increasing my volume of that gas as well. And so Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law all combine together to make the main ideal gas law, which is PV equals nRT, which P is the pressure, V is volume, N is the number of moles, R is the gas constant, and T is temperature. So for this particular presentation for active learning, I will first go over what is the research-based evidence that backs up active learning. And so first, it states that there is intentional construction of skills, abilities, or knowledge through participation or contribution. So this is that the students are taking responsibility for their own learning. It's not necessarily just complete direct instruction that is teacher-centered. This active learning is rather more of a student-centered approach to learning, and that there is a requirement of high levels of involvement in information gathering, analyzing, and problem-solving processes, which are all the concepts that are needed within the area of chemistry to fully understand it. We need high levels of involvement and high levels of thinking. And next, it encourages reflection upon ideas. So reflection could be writing in a notebook. It could be reflection questions in particular, which I will have at the end of this presentation. Or it could be reflecting upon data that is collected, which is what we will also be doing in this case also. And it also includes regular assessments of individual understanding and skills and handling concepts in a particular discipline. So this is assessing individual student learning at particular skills and concepts that are needed within the area of chemistry. So for my particular demonstration of active learning upon the ideal gas laws based on gas properties, the topic is the ideal gas laws based on gas properties. And this particular example I'm going to use is actually over Gay-Lussac's law, which is actually going over the relationship between pressure and temperature, keeping volume constant. And so the implementation plan is through technology-based learning, which will be utilized through a PhET simulation of one in particular called the gas properties. And the teaching demonstration will go about more of a project-based learning activity where students will work in cooperative learning groups. And within the simulation that the students will work with in these groups, they will keep certain gas property constants the same. They will change their independent variable, which is the variable that you are manipulating. And then as we manipulate and that independent variable and change it, whether we increase it or decrease it, the students will then analyze what change occurs within our dependent variable, which is the one that we are studying the relationship with. Then we will collect and record the data of the particular gas properties, and then through that we will graph the results and analyze and reflect from there. And so our guide includes the access and instructions to get to this PhET simulation, and also through Microsoft Excel, where we could make a table within our data. We can make a table of this is our dependent variable, this is our independent variable, and then we can make a graph of our x-axis is our independent variable, our y-axis is our dependent variable. And then there are also reflection and application questions at the end to guide student learning. So again, with our active learning method, we have an online laboratory simulation, which is also based on project-based learning, to analyze gas properties, which then conclude with ideal gas laws. And our resources is that the students would first have access to this simulation through phet.colorado.edu. And under the Simulations tab, they would click Chemistry. Then they would click on the gas property simulation in particular. Then they would click the play button that would pop up in the center of the screen. And then a bunch of options will come up after that. They would click on the one that says Ideal to then begin the simulation. And another resource that the students would have after they get the instructions to get to the simulation would be Microsoft Excel, which we will use to collect our data, make a table, and also graph our data. And so the example of an instructional component that you could use for active learning would be that the students would have this following prompt. That could be through a PowerPoint presentation, for example. And the prompt could be, analyze the relationship between pressure and temperature. Let temperature be the independent variable in this experiment. And so what the students will first do is that they will have a set of instructions here through the presentation, through their active learning presentation in their cooperative learning groups. It would first tell them to use a simulated air pump in the simulation to add one set of heavy air particles into the simulation. Then from there, they will check mark volume under the hold constant section. And then as they are collecting the data, they will let the simulation run. Then they would click the pause button to then pause the simulation to where they can then record pressure and temperature at that constant volume. And then after they record the data, then they will resume the simulation after the data collection, let it run more, then keep collecting data that way, pause it, record your data. Let it run, pause, record your data. And so this prompt would also add, well, what happens when ice is added to the simulation, and what happens when heat is added to the simulation in particular. So for example, this is a screenshot of what the PhET simulation of gas properties will look like. So for example, students will take this air pump, and they will pump one set of the heavy air particles into the simulation. So for example, we would click this blue one here because it is the smaller air particles, that's the heavy particles. And then they would just pump it one time. They will pump the heavy set of the air particles into the simulation. After they click play, they're going to keep the volume constant. So under hold constant tab here, you would click volume because volume is not one of the gas properties we're analyzing. We are analyzing pressure and temperature, just as the prompt stated. Then we would play the simulation. We would see what happens. In the first prompt, the first reflection question in the prompt asks us, well, what happens if we would add ice to the simulation? So that is temperature. We are going to manipulate temperature, which is our independent variable when we graph the data. And so under here on this bucket, there is the red part and then there's a blue part. And so what you will do is you will, if you're wanting to add ice, which would decrease the temperature, you would just take that little bar and the students will click on it and slide it down into the blue section. So it would be in this area. And once they do that, this is the temperature reading. The temperature would then decrease. So this is where you would read the temperature. So the simulation starts at somewhere around 300, 310 Kelvin. And so after I added so much ice, it is around 196 Kelvin now. And then I would record the pressure here, which is my dependent variable that I am analyzing. So the students would record it. So for example, here at 196 Kelvin, that would be the temperature that the students would write in a data table. It is at 4.0 atmospheres. The pressure is. Okay. So then after the students pause it, record the data, then they would click play again, add more ice to the simulation to see what happens when you decrease temperature, what happens to the pressure, pause it after it runs, then record your data. And then this is an example of the second reflection question that was stated of what happens whenever heat is added to the simulation. So instead of adding ice, which would be holding this blue bar here and putting it here in the blue section, I would take the blue tab in the middle and I would slide it up into the red portion. So then heat would be added to my simulation. Again, I'm still holding volume constant. Whenever I would add heat to the simulation, my temperature went up. So I added heat until my temperature increased to 281 Kelvin in this particular case. And then from there, the students would let the simulation run. After it ran, then you would hit the pause button to help record data. And then, for example, at 281 Kelvin, the temperature, my dependent variable, the pressure, increased to 5.8 atmospheres. So that would be one of the data points that the students would record in a data table. They could even record it in a laboratory notebook, just for the reflection part of this active learning. So for an example of the data table and the graph, that this would be the data table that was created through, you could do this through Microsoft Excel. First, the students could even write it down in a laboratory notebook to help them, and then they would record their data through Microsoft Excel. So for example, my independent variable, the one that I was manipulating, temperature in Kelvin, is here on the left. Then I have my dependent variable, the pressure, is on the right in atmospheres. And this is the first set of data I collected when I kept adding ice. Okay, so I would start at 300 Kelvin, and then it kept going down as I added ice to the system, all the way down for, in this particular case, 195 Kelvin as the temperature decreased. But as temperature decreased, there is a trend here of the relationship that as the temperature decreased, so did pressure in return whenever you keep volume constant. So when the students go to graph this on Microsoft Excel, just so it's not time consuming to do it on a piece of graphing paper, do it through Microsoft Excel for technology-based learning, the temperature in kelvins would be on the x-axis for our independent variable, and our dependent variable would be graphed on the y-axis, which is pressure in atmospheres. So here I am graphing the pressure versus temperature. And here I have a line of it going up, because if I increase the temperature, then the pressure increase. Likewise, if I would decrease the temperature, adding constant ice, I am decreasing the pressure. And then also I included my slope-intercept formula. I included an r-squared value just to see how close we were with the data. And we have a nice line here that is increasing, which is telling me that, and telling us with our data, that temperature and pressure are directly proportional in this case, which goes along with the law. And then here is an example of the data table if I was adding heat to my simulation, which was that second reflection question in the prompt the students would be given in this case. So again, I made a data table. I have temperature here on the left. I have pressure here on the right. Again, temperature is the independent variable. Pressure is the dependent variable that is being analyzed. So because of that, temperature in Kelvin is again graphed on the x-axis. The pressure is graphed on the y-axis. And I have the same thing happen. The same exact thing happen. Whenever I increase the temperature, the pressure increased as well. It went from 5.8 atmospheres all the way up to 7.6 atmospheres at 417 Kelvin. So again, I included the slope-intercept formula, included an r-squared value for the data. But again, students will come to the conclusion that the temperature and the pressure are directly proportional whenever volume is constant. Okay. So then the following could be reflection questions that this teacher or educator could add to the active learning presentation to help with student learning. And so the first one is here, what conclusions can be drawn from the relationship between temperature and the pressure of a gas? And so just as I stated, they are directly proportional. If one increased, then the other increased as well. And the second part of that question is, well, what ideal gas law supports this? And that's Gay-Lussac's law, which is also known as Monton's law. It is also known as, and that is whenever pressure and temperature, again, are directly proportional. And another reflection question is, well, why is pressure located on the y-axis, but temperature is located on the x-axis of the graphs? And that is because the temperature was our independent variable and pressure was the dependent variable, which is important to the scientific method for any area of science, which is needed in the area of chemistry. And another question could be, well, if volume was the independent variable and temperature was the dependent variable of a graph, describe which variables will be located on both the x and y axes. So for example, in this case, students could draw the conclusion, if volume is the independent variable, it would need to be on the x-axis. And if pressure is the dependent variable, it would need to be graphed on the y-axis. And that could be another part of the active learning that an educator could go into, where students could then analyze the pressure and the volume of gases. And another reflection question could be, if volume and pressure were the gas properties being analyzed and graphed, which gas property would need to be held constant? And if we were wanting to analyze volume and the pressure, we would need to keep temperature constant. So in that simulation, if the students were wanting to investigate what happens with pressure and volume, they would need to keep the temperature constant. And the second part of that question is there an ideal gas law that supports this? And if students would go about working with volume and pressure, they would then learn about Boyle's law in that case, which states that volume and pressure are inversely proportional to each other. For example, if we would increase the volume of a gas, then the pressure would in turn decrease. So thank you very much for listening to my active learning presentation, and here are my references.